If you want to learn more from data, being able to introduce a little bit of physics, you can either learn more from the given amount of data or you can learn with less data.
Welcome to a brand new episode of our podcast, Human and AI, Mind, Machines, and the Great in Descent.
Thanks for tuning into our geeky podcast to discuss the fascinating field of AI and machine learning, corporate craziness, passion for technology, and the role of humans. We are Uli and Abri, your hosts for this episode, and we're extremely grateful and excited for today's star of the show. He is an AI innovator, strategist, and business leader who aligns technologies with customer needs to create new business opportunities. And I'm talking about none other than Amit Chakraborty, the principal scientist for physics aware AI. And he has led multiple strategic AI and deep learning initiatives, combining research experience, engineering expertise, and market knowledge to develop new products and services. So I can't wait to learn more. Amit, welcome to the show. How are you and where do we catch you today?
Thank you very much, Uli and Arbery. Uli has been a very long friend of mine. I have known Uli for a very for an extended period of time, probably going back at least 10 years. And Arbery, it is a pleasure to meet you. It's morning here in Princeton, pretty hot day. Uh, and yeah, I'm happy to be with both of you. Really excited. Hopefully, we'll have some interesting discussions.
Yeah, I mean, fantastic to have you actually. And you were one of the first when I started kick off my somehow engagement with Siemens. One of the first, I was sent to Princeton
Yeah.
and meet you. So that's, for me, you're somebody I look up, to be frankly fair. So I think it's super honorable to have you actually and continue to engage in have a conversation with you. So we've, doing machine learning, then we always try to, explore it, a bit of finding patterns of the past to explore it in the future. One of these typically correlations that we find is a correlation of music and technology passion, right?
Hmm.
So, and we're wondering which does it apply as well? Is that are you playing any instruments? Are you passionate not only in technology but also a bit of music? What is on Amit's hot rotation in the evening when you get really chilled and relaxed?
Um, Yeah, yeah, music is. I really enjoy music, in particular Indian classical music, and maybe a little bit the semi-classical version. Um, and that is actually a gift from my wife because she is a professional uh, musician of the Indian classical variety. So I get to hear a lot, and from her, of course, I also listen to all the other big, maestros in this particular genre. So yeah, I like music, but of course, I have my other hobbies are politics and finance. So those are the things that keep me occupied when I'm not thinking about machine learning or work in general.
So music, politics, finance, and technology. I like that a lot. When we found out that we would have you as a guest, we of course did a little bit of research, and we found out that you studied in Yale, and afterwards you joined the Siemens family, and ever since, so for the past 26 years, you've been shaping the company with your innovative spirit, your creative mindset, and your broad expertise. And that resulted in a very, very impressive track record. So you ran numerous projects, filed over 40 patents, and are the author of over 50 publications. And in 2021, you've even been awarded the Siemens Inventor of the Year for your lifetime achievement. So congratulations and chapeau. Amit, what's the secret sauce behind your thrive, and what is it that really drives and motivates you?
This is an interesting question. You won't be surprised to learn that this was also the question that was asked when I was given this award. And my thing has been that there is no real secret sauce. I'm really proud to have had a long career with technology, because as Uli also knows, he was a little bit for a long time partner in crime, and so to speak. You get to work with a variety of business units, and all these business units are, in some sense, unique and have their own problems that are somewhat different from each other. So working with these varied business units and on their problems will always keep things interesting, because you get to work on a whole plethora of problems, that needs new thinking, new ways of doing things. So yeah, I mean, that is certainly something that keeps things interesting. Also, the fact that we get to work with universities and national labs is another interesting facet of what we do. As I said, that also is something that I treasure, and I'm sure most of my colleagues do as well. And finally, of course, the fabulous colleagues. We have Willie here, but there has been a lot, and there will be a lot more. As they come along, they come with their new ideas, and you learn from them. And sometimes, of course, you little bit mentor them as well. But it's a constant learning experience, and if has to be a secret sauce, that is probably what it is. So interesting problems, interesting people, um, and interesting associations externally and internally.
Yeah, awesome. Lifetime achievement. Oh gosh. How old do you feel with that, right? You're far from, being at the end, right, of your work, but that's really awesome, really
So
dope.
yeah,
Eh,
it's a great honor.
It is.
It certainly is a great honor, and
Mm.
I'm glad that Siemens has recognized me as such. And of course, I'll have to. Of course, that also means the expectations are high to keep things going at the same rate
Yes,
or
yeah.
even more. So,
Yeah, absolutely. So you're now a principal scientist, right? It's a technology,
mhm,
right, from a position itself. So one of the most tricky things, I guess, on the conversion between academia and business units, right, shaping and extending state of the art is, the role of an expert, or, he or she, right, expertise, right, because it's somehow super
mhm.
difficult, how to measure actually an impact. Everybody, management demands you want to have an impact on the organization, you want to have impact on view, on problem, right? So how do you say what is for you an expert, right, in a corporate ladder, right, and in a corporate world, and how is impact somehow measured? That's a tricky one, isn't it? Every year we had the same review, right?
It certainly is a tricky one. It certainly is very tricky to measure things.
Yeah.
But let me first try to answer the first part of your question. Um, in my mind, all of us are experts, right? We are professionals at what we do. We are experts at what we do, and that is part of the reason why we are here, right?
Mm,
As a PKE or principal key expert, my role is one to defining the roadmap for a specific technology, and work with colleagues to secure it for Siemens. Of course, that's a very general definition, right? And of course, along with that comes the need for proper empowerment. I mean, experts can only do so much if without the proper empowerment. Now, now coming to your question of impact, right? Impact needs to be measured both inside and outside of Siemens. Um,
mm,
so sure, you can. One easy way would be to measure by just looking at the total volume of revenue generated. But we are not just measured by total amount of revenue that we bring in. We are also measured by the innovativeness of the problem. Right? It's a problem is a might be very innovative, even if at that point the business value might be small. Also, experts are the ones who should protect an organization from, protect an organization from being disrupted. So they should come up with the disruptive technologies, or be aware of the disruptive technologies, and try to either disrupt or take proper action, so that the organization doesn't get distracted or disrupted. So yeah, I mean, measurement will always remain a big problem. But I do think the acceptance of a certain type of work, both inside and outside of Siemens, it's holistically looking, that should be the way experts are measured. Now, of course, for some technologies or some people, it might be more internal because of the way
Mm,
that particular field is defined. For others, it might be more external, but eventually both would be needed. That's my
mm.
opinion. I mean, of course, every
Yeah.
you ask everyone, I'm sure they will all have their own ways of defining things. It's a very
Mm,
subjective
true.
thing. It's not. We have no clear objective approach to defining these things.
So let's talk about AI and a bit of machine learning. So we've,
Mhm.
at the very early stage, right? We did stuff together also on information retrieval, was about text heavy stuff, QA stuff, question answering stuff. Then, you moved with your team more into predictive stuff, and even, so actually quite a variety of, the application of machine learning methodologies, right? In across all the business units, right? How do you see has the last years somehow developed, right? The machine learning community, and can you share a couple of, maybe some cool projects, you were affiliated to that? It's like, that's pretty dope. That's what is machine learning. This is what maybe AI, what industrial AI is for you.
Mhm. Initially when we got started, if you might remember that um, a lot of the things the way we are using, maybe I would say advanced machine learning, it was somewhat of a exploratory nature. Now, of course, it's no more exploratory. It's a mainstream. There
Mm,
is a requirement to make sure that almost all products that Siemens produces, have a particular AI roadmap. So I would say AI has moved mainstream. That certainly is the case. Also, when we were looking at it like 10, 12 years back, deep learning was just getting started. Now, anyone and everyone who dabbles in data considers themselves to be a deep learning practitioner. Whether they become an expert on deep learning or not, that's a different discussion. But in general, in some ways, deep learning and machine learning in general has been democratized, and everybody is using it. And to an extent, there are many platforms, many easy ways to actually use it. So I think it has evolved quite a bit to the point that it's hard to find an organization that is not relying on deep learning for one or the or machine learning in general for one or their other problem. AI is ubiquitous at this point, right? Now, of course, very interesting problems are coming along. In terms of some interesting problems that we are looking at, of course, you will remember from the problem from the projects that we did or the platforms that we built, there were interesting problems, not in different aspects of predictive maintenance. We had aspects of parts optimization. So there was some supply chain optimization problems we looked at. We looked at the problem of trying to get people prepared for field engineers prepared for maintenance tasks. So there were a lot of problems that we are looking at. So we were trying to build a platform on which many AI applications could sit.
mm,
Recently, of course, coming back to my physics-aware AI topic, right? And there are some very interesting problems that you're looking at. For example, this recent problem that we looked at with DISW, which is the software as a part of DI, along with their customer, which is Daimler. We were trying to look for how, for example, you can use machine learning to create a surrogate model of the cabin, that a car cabin, so that you can try to um, optimize the comfort level such that the driving distance or the car, is also maximized. So it is a joint optimization problem where we try to optimize the comfort level as well as try to increase or maximize the driving range. So that's an interesting problem that we looked at. And for that, of course, one traditional way could be just you run a lot of simulations and do it. Our approach was one of creating a physics informed AI surrogate model that can be used to run this simulation. So it goes towards the problem of design automation or being able to design space exploration. And now, for example, we are doing that. Design space exploration needs there is a collaborative aspect to it, and we are looking at that in a recent problem that we are doing in across multiple TFs. And here the more problem is one of course, looking at the entire car and trying to design some aspects of it in a collaborative fashion. And for that, as you can imagine, you need to have a proper you need to run a lot of simulations, but of course you cannot do that because simulations take a lot of time. Hence, and one approach to that would be to create a surrogate or a machine learning based model that can be instantiated or evaluated almost instantly. So, then another example in this direction could be something that we are looking at, which is to design interesting materials with certain material properties. So it's a kind of a reverse engineering. So the material properties that you're looking for, and then you try to go back and find out, what kind of manufacturing process would you use to create that particular material with a certain set of properties. So there are many many interesting problems that we are looking at, or the ones that we could look at. And this is not just in Siemens; outside of Siemens, also, as you are aware, there are very interesting problems people are looking at.
And from all of those, which project would you say was your favorite or the most shaping project that you've been part of?
I would say that the battery life extension problem, or that is very interesting. Why? Because it was of high value. It was interesting both for Siemens. That is supported one of Siemens customers, in this case Daimler, and there are other customers were also interested. So that is interesting, but by no means I would say that's the only problem that one can look at. It was very interesting from a personal point of view because it was the first of its kind for me, not in general, but for me it was a first of its kind. But you can take the same problem to the buildings, or maybe even a train. So there are many other directions that you can take this particular problem.
Um, yeah, you just mentioned a range of different AI applications in the industry. And what makes them so exciting is that they can have a real impact in the world, and that they can be used widely, and that they can also scale largely. But on the other side, and I bet you also face the problem, we often lack the sufficient quantity of data, though we need to make use and inject domain know-how into the ML model somehow. So, what are the ways how to add explicit, or at least somehow explicit, knowledge in the world of machine learning? And I'm thinking in the direction of maybe simulation or graphs or even synthetic data or something like that.
So I'm glad that you're asking this question because that somehow relates, or the approach or the methods that I'm recently looking at as a part of my physics over AI roadmap directly lead to that. And one of the things when for machine learning, when you try to do, you need a lot of data so that these methods generalize well, and also they work. They have low errors, right? So have high accuracy. So however, it's known, and as you correctly pointed out, there is always not enough data. There's always a lack of enough data. So one way, and a lot of people are looking at this, for example, is to look at inductive. How do you introduce inductive bias? Inductive bias could be in the form of known physics, in the form of known domain knowledge that exists, or constraints that come from just because of the physical limitations of the environment. So inductive bias could be a variety of different things, and all of these actually, once you are able to introduce inductive bias, you are able to generalize better. You can work with you can work with less data, and yet have achieve better accuracy, and on the other hand still find a way to generalize better. And these inductive bias have been used in a variety of problems, from flow modeling, control, economics. There are many areas where people are looking at inductive bias, use of inductive bias. And just the purely, if I were to say, physics aware AI is more looking at one aspect of it, but eventually people are looking at a variety of different problems where inductive bias could be very, very relevant. And I'll give you one example, and I know it might bleed into other questions that you might have for me. Um, I was listening to a talk by Professor Michael Jordan from Berkeley, and I'm sure Ulrich is very aware of his work. And he was saying that he was looking at machine learning as a evolution of machine learning in four different steps. Um,
Mm.
in the I don't know, Uli, if you are aware of that talk, or if you have seen that talk. If you haven't, it's a very interesting way the way he looks at it, and I happen to feel very comfortable with the way he did that. So in his mind, the first generation of machine learning, which roughly spanned 10 years from the 1990 to 2000, focused on, let's say, search, supply chain management, fraud detection. And out of this came the likes of Google, Yahoo, and others. Yahoo, of course, disappeared, but it's still there in some way. The second generation started into some aspects of the human side, and that included, for instance, that's how you ended up with the likes of recommender systems, e-commerce, social media approaches. So not just backend data modeling, but you actually start introducing some human element into it. And from this, actually, if you think about it, that also lasted about 10 years, from 2000 to 2010. Um, and came the likes of Amazon, Netflix, and even one can argue Facebook, or now Meta, right? Meta is, of course, relates to a much later thing. The third generation, and this coincided with the onset of deep learning. And Uli, remember, our journeys, was the project that you started off with the interview, was in
Mm.
this particular phase. Um, Coincided with the deep learning, and interesting applications in computer vision, NLP, speech processing came along. So and the new, or the emerging piece that is happening, is more about the use of machine learning for a variety of problems that include decision support, markets, and so on. That includes multiple agents. Of course, physics of AI is part of it. Decision making using some game theoretic aspects, Internet of Things. So this is a very interesting way he looks at it, and it's a very not just physics of AI. Another interesting example that I learned was one of, and this is comes on our regular on a regular basis that we see. Let's say you are looking at a problem that can be modeled using a multi-IAM bandit problem, right? And just think about, it's not just about pulling one of the levers that you have, but you also are aware that that you might have a competitor out there who has certain preference for certain levers, right? In
Mm.
that case, you bring an additional context to the problem, which says that, okay, you cannot simply you cannot ignore, and depending upon who the other guy is, or you will have to adjust your strategy. So
Yeah.
traditional problems getting defined, or because of market interpretations. In this case, multi-bandits are used in a lot of market problems. So anyway,
Uh,
I think I
uh,
digressed a little bit and gave a lot longer answer to a short question. So um,
Absolutely, no worries. So I love this spectrum, right, from backend to human side to pattern recognition towards market. Does that mean actually that we are ending up at the multi renaissance of a multi agents systems again, right? Like a plethora of agents, making decisions. Is that the difference?
Yeah, it could very well be that. I mean, of course, none of us know the future, right? But
Mm,
multi-agent systems is becoming more and more common because of the fact that we want to live in an intelligent world, but there is no one single place where all the computational power can be, or all the, you cannot have decision making centralized. So you have to live with
mm,
decentralized decision making. You have to rely on this world of Internet of Things. You cannot say that all the Internet of Things is a bunch of dumb sensors. That's all that is there to Internet of Things. It's probably going to be a lot of intelligence along the way. So in that sense, multi-agent systems is could be very interesting. In fact, we may have to relearn a lot from the from how nature actually does things.
mm,
And I think multi-agent systems are there in nature everywhere. You look at how how, for example, this group of birds fly, bees,
mm,
ants.
mm.
You can learn a lot from them, and of
Sparks.
course, we have learned from them. Some of the early optimization, heuristic optimization problems used in mixed integer optimization is basically swarm optimization methods, right? That
Mhm.
come from this.
And I guess that poses some challenge to problem solvers again, right? No, but
Or,
let's
or
let's
maybe
jump on.
maybe or maybe as
Yeah,
support, they
yeah,
you are looking at ways from which
mm,
you can gain insight how to solve certain problems. I mean, if you think
mm,
about we are looking at the stock market on a regular basis. I'm going back to my finance example. It is a multi-agent system, right?
mm,
It's a
mm,
many. I mean, in some sense, a lot of people say that the market is more intelligent than every single economist out there, right? Why? Because
mm.
it's a collective wisdom.
So let's bring it that you mentioned a couple of times, right, that your specialization is sometimes, it's you're mentioning it as physics aware AI, right? Sometimes I hear physics informed. Sometimes others call it hybrid models, right? So for the
Hybrid
audience
AI.
out there, yeah, hybrid AI, right? So for the audience outside, right? What does it actually mean? And how can one envision what is this thing, right? Is it we're fueling a lot of more data in there? Probably not, right? What is it exactly? Can you make it a bit more tangible for
Yes,
the audience?
sure. I Let me give it a try. I hope it becomes simpler. So the first thing is, what is it, right? As I alluded to earlier, it is the introduction of some form of inductive bias into a machine learning problem. Now, let's try to make it even more simpler, right? At the end of the day, every single machine learning problem can be modeled as an optimization, right? Every single machine learning
Mm,
problem, more or less the ones that we are aware of, are solved using some form of optimization. So, so the problem is one of solving an optimization problem that could be high dimensional. It could be nonlinear. It could be non-convex
mm,
or multi-scale. So it's all the complexities that you can think about, right? And now, where does the physics come from? It can come from simple observations of nature. For example, conservation. There are conservation laws for mass, momentum, energy that we have all learned when we were kids, right? There are
mhm,
also symmetries in natural symmetries that exist in nature, right? We can learn from them. So if you take a optimization problem, introduce these physics laws one way or the other as constraints, as soft constraints, hard constraints. I don't think it's important to get into that. And together, if you are trying to solve problems for dynamical systems, for design or discovery or prediction and control, that might, in my definition, that's what physics aware AI is. Now, of course, dynamical systems, by that I say it in a very general way. So a market is a dynamical system, human body is a dynamical system. Um, a plant is a dynamical system. So you can, I think I'm just trying to make a very, take it at a very high level. Now, when it comes to modeling, these simplify, basically we need to exploit these simplifying transformations. And as I said, simplifying transformations can be nothing more than symmetry, and and explore these hidden patterns. And so I'll give you a very nice, interesting example that I think everybody can relate to. But before that, it would be incomplete and inappropriate for me not to mention the fact that much of the basic theory has been there for a long time. In fact, if you go back to the time of Jacobi, Hamilton, Poincare, they came up with a lot of these ideas. In fact, it's a as an interesting anecdote, Uli, you are living close to Erlangen, and you will probably know that one of the most well-known mathematicians from Erlangen is Noether, and she has a very interesting theory that relates or equates symmetry to conserved quantities. And today, much of physics aware AI is looking at exploiting this particular theory, how you bring this particular symmetry as a conserved quantity that becomes a part of the inductive bias. So that's a very interesting one. Now, as an example, right? Um, One very interesting example is what I have seen is to look at, for example, this concept of what people call let me take a moment. People call heliocentrism to geocentrism. Okay, so what do I mean by that? By that I mean, whether, let's say we are looking at the planetary data, right? As the so as planetary data is all about information about the planets moving right around the sun, obviously. But if you look at that and you put Earth at the center, if you plot that data, you'll get a jungle. But if you plot that same data with the sun in the center, right, you get a
Mm.
very nice observation, and from there you can deduce a lot of things. But when you take the same data with, so why do I say this is interesting? Because it's a same data with slightly different. With in one case we are introducing a little bit of physics knowledge. In another case we are not, right? Or in maybe you can say the incorrect knowledge, and what a difference it makes. So what I'm trying to say, if you want to learn more from data, being able to introduce a little bit of physics, you can either learn more from the given amount of data, or you can learn with less data. So that, in my mind, is physics aware AI. I hope I've given you a good example, and I also give the definition right. And there are many problems left in physics aware AI for Siemens. Siemens is where you see physics aware AI. For of course, we spoke a little bit about. Uh, Physics aware AI problems in flow control, but any multi-physics simulation, turbo machinery, design and control problems, because energy preservation is a very important thing in control design. Grid control, where you have the Kirchhoff's laws,
Mm.
even positive train control, because when you try to control the train, you have to use Newtonian physics, right? Friction and all of those. So it's everywhere.
Amit, that was beautifully put. I'm very amazed that you, like, by using the planets, you explained us what physics aware AI is about. Very, very well put. So, when we talk about machine learning and AI, especially in the industrial context, what's highly important also with regards to the increasing use of AI and infrastructure in different products or processes, the aspect of industrial grade AI is crucial and it's getting more and more attention. And industrial grade means like robust, explainable, but maybe even verifiable. So, in your perspective, so what's explainability and verification of ML and the ML ops lifecycle? Like why? Like what's your view on that? Is it highly important? How can we ensure that?
Clearly, it is very important, right? The thing about, as I told earlier, right? When we were when Uli and I were getting started with this very interesting project of platform development, deep learning was in its infancy, and now, of course, it's a very mature area. Um, and now it wouldn't be, if it was not for the research that went along in this area of introducing explainability, different approaches to verifiability, as well as this ML ops, right? These are the ones that have made this, I would say, that have moved AI or machine learning or deep learning into the mainstream, because there is no way anyone would accept, or if a black box decision making, and we knew that even at the beginning, then, right? There was initially a lot of the decision making, um, it was basically machine learning was used as a way to support that, and not as a way to actually make a decision. So, but now, of course, explainability. There, I'm personally not focused on explainability research, but I know that it is a very important aspect, and people try to create networks that can help. That can focus on the explainability part. So, if a decision is made by a neural network, it must be able to say where the decision is coming from, for example, which particular feature is responsible for that, and which, even sometimes they want to even find out which data points are the ones that have led to that. So explainability is very important for the acceptance, right? Now, validation has always been, but an important aspect of data analysis. Now, of course, likewise in machine learning, also validation and verification is important. So I don't see anything new there. um, the MLOps is basically that is just a sign of maturity, right? Just like, DevOps have become the way to develop complex software systems. MLOps is basically what is making or democratizing the use of ML, and doing it in a way that keeps things efficient. So, I think these aspects are just a sign of the maturity of the field. And of course, the use of it in every aspect. So, yeah, of course, if anything, these things are going to become even more important going forward,
Mm.
as ML becomes more and more entrenched in every aspect of our life.
Yeah, but the question is still, is I guess if we need to scale, it needs to be somehow auditable, right? And it means,
Yeah.
is a machine learning system 100% provable, reproducible, even, in terms of these scores? And do we need to include, this, or is it part already of the game of software, right? That adding this non 100%, probability of, of such systems, is part of the risk, and we need to live with some kinds of level of
Some
risk.
of it, yeah, I would say some of it will have to live with some of the risk, because on one hand, if you think about it, there people are looking at larger and larger models that would make it very even for some problems you actually need these very large models, right? Now,
Mm,
uh,
mm,
none of the models are, if you have very large models, explainability becomes more and more complicated, right? Verifiability not
mm,
so much, but explainability for sure. So you might become, it's only some, not every single large model is easily explainable now, but of course they might be needed. Now, in terms of, there are people have adopted freely from the control literature to introduce aspects of, you know uh, stability, robustness, where there are provable guarantees
Hmm.
for certain, as stability and robustness that people have brought in from the control literature. For example, in control, there is the concept called Lyapunov stability. Now, you people have for certain control problems where machine learning is used, you could constrain the problem to be provably stable. Now, obviously that means that it is going to be stable, so you, because mathematically you can prove that it is stable, so that takes care of this. Now, but I do think for some very large problems, people will accept it as a part of the risk, because when I was doing my PhD, I was focused on medical imaging as my topic, and even there, we had to, for certain verifying the results, for, let's say, we used to do image analysis, and then we have to validate them, right? So we had to look at, we used to draw from the expertise of the doctors in the medical school. And if you ask 10 doctors, you will get you will get a probability distribution of their results. So in a way, when you go to a human expert, you accept the fact that it comes with a certain amount of risk, because even the best expert is not always 100% certain. So in my mind, um, but on the other hand, for some problems, even the best expert just doesn't have the bandwidth to do it. For example, recently, I think you might remember that there was this paper that came out, or rather, Google released the database of all known proteins. Right now,
Hmm.
probably there is not a single researcher in the world who has this is somewhere around 200 million proteins. I mean, every people, I know researchers in this particular molecular biology area who spend their entire life working on one or two proteins their whole life. Just think about the
Hmm.
fact that Google has able to look at 200 million proteins. So now, for that particular model, is are we trying to going to make it very lean model that is explainable? Maybe in the future, but for now, I think people are happy to see that it is at least something that is doable and has a certain level of accuracy. I don't know if I answered your question, but of course,
Yeah.
it has no clear answer, right?
Yeah, and kudos here actually to DeepMind, which submitted the entire thing as a pip
Yeah.
install AlphaFold, right? So
Yes.
kudos
Yes.
here. That's pretty dope, right? Suddenly you have this amazing
Because they
source
want to
control.
democratize that particular field, right?
Yeah,
And it's a very good thing that has happened.
yeah. So coming back a bit of the trends now, right? If you look a bit in the future, right? Studying the a bit of XRFX, I guess you are now in the machine learning papers you contributed. We see, I don't know, the last year is pretty dominant. A knowledge graph will be the hot turf, which will be pushed through the corporate and as well as research level. Then following up with graph based machine learning methodologies, right? A lot of things. The last, I don't know, the last 2 years conferences were all about transformers. Whether you're on CVPR or whether on others, right? It doesn't have to be image per se, but everything is all in transformers architecture somehow. So what's your bet? What's the next big thing here in this research field?
It's always very difficult to predict something, but I think in this case, I would go with my previous convoluted answer that I gave, where I was trying to, take the cue from Michael Jordan, whom I really, really respect, and I like his interpretation of things. And as I said, physics-aware AI is a aspect of it, but I think
Mm,
there is a lot more to be done in terms of, exploiting the laws of nature. So let me put it
mhm,
this way: laws of nature or laws of market. So from that angle, I would say being able to introduce this inductive bias that comes from a variety of directions, and solving problems that until now was impossible to solve, basically is going to be the future, and it's already happening, right? People are looking at physics, these introducing looking at physics as a way to address flow control problems. We are looking at just think about how nice it would be, um, if we can mimic, if airplanes could optimize the energy usage in the way an eagle or some of these majestic birds fly. Of course, we are far from that. We cannot. I mean, there are people looking at how Drosophila, or very humble fireflies, even just to model them, all the somewhere around 200 or 300 neurons that they have and how they fire in certain different circumstances itself is a huge challenge. So but I think that is where all the interesting things can. I mean, at least we deep learning has given us the mechanism to do that, right? So now those are the ones. That is the direction that people will probably take. You just think about how much deep learning has, or machine learning in general, has penetrated the world of economics. Very little.
Mm.
You have supply chain problem all over the world. Just think about, there are ways that, there are ways to go before those problems can be handled. There are many others like that where molecular dynamics could be very interesting, trying to come up with models of designing materials, as I said, that have certain specific properties down from the molecular level. People didn't have the mechanism to do it. Only now people are able to do it, thanks to the groundbreaking work of the of Google DeepMind, as we said, in the AlphaFold, or other problems like that. So I think, from that aspect, I really do believe in what I'm doing and the introduction of inductive bias. So I think that could be the next thing. Maybe I'll be proven wrong after some time, but I think so far I have no reason to think that I would be wrong, because the trend seems to validate that. Because And also this use of more and more data. You not only look at this day, the AlphaFold and the Google's work, but also whatever work is going on in the general area of self-driving cars. Um, as I said, near time or near real-time simulation of flow control. And
Mm.
the other day I learned about another interesting example that is done by none other than our own health idiots, which is basically, as you are being imaged in an MRI machine, right? You can almost real time figure out what other aspects or other imaging, other areas of your body, or needs to be, or where you need to focus the imaging. In addition, this was unthinkable while the patient is in the MRI. And how why you can do it? Because you can process billions of images at a time. So machine
Mm.
learning has given us these capabilities. Now it's a matter of imagining and coming up with um, interesting applications. So these applications can now be enabled. Now that we have the
Mm.
infrastructure, we have the ability to do so. So that's what I think. Where the future would be, to use more and more data. In some cases, in other cases, probably to exploit more what we know, what we can see and learn from nature.
Amit, time was really flying, and we already reached the last question. And now you shared a lot about what you're doing professionally. And now we're also curious, especially with regards to your background, that maybe there's some things you could share with the audience, since you gained tons of experience in the industry as well as in academia. You held various leadership roles, worked together with different types of people in different places in the world, and maybe there's some advice that you have to give genius minds out there who are crazy about ideas, or who would like to, yeah, become better leaders. So yeah, what would you tell those people? Are there any advice that you would like to share?
I think, as far as the advice goes, I would say, in my mind, three things are very important. One is patience, right? As youngsters, people often lack that, and make decisions, or that they really in future don't, maybe not, I wouldn't say repent, but maybe in hindsight is not the best one, right? The second thing is, of course, accepting change. I think we all have gone. Any of one of us who have been around for a little bit have seen that. Today the world is very different than the one from which we when we graduated. So things constantly change, and you have to accept that. And along with that comes the need to continue to learn new methods, learn new approaches, learn from others. So all of those are very important. So that's what I would say. Nothing extraordinary, very simple. Yeah.
Beautiful and very concise. And with that, we move to the last part of this episode. And
Hmm.
so, Amit, first of all, thanks so much for your time. We know how busy you are and that you took the time to share all these insights and experience with us. It was a great pleasure. And
Same
for
here.
the closing, we always have a little game, and it's called Authentic Autocomplete. It's Uli's favorite game in the world.
Hashtag
And
trademark. Hashtag trademark.
and
Yeah.
for the
Yes,
closing,
trademark,
I
huh?
would love to give you yeah, a couple of sentence starters, and I would like you to complete them. So, Amit, are you ready for this challenge?
Let's give it a try.
Let's give it a try. So, let's start with an easy one. Siemens is
I would say a very dynamic organization, and for an innovator with the right mindset, a great place to work.
amazing. Physics aware AI is
I think I've already answered it multiple times, but I'll try again, which is physics aware AI is introducing inductive bias in the form of known physics within a machine learning framework.
so easy in one sentence, right? Technology with purpose is
Solving technical problems of high business value.
There we go.
beautiful. Innovation is
Finding the best solution for a given problem, which often leads to new way of doing things.
amazing. And last but not least, if I could invent a rule for everyone in the world to follow, it would be
To keep things simple.
that was simple for sure.
That was simple for sure, I would say. Hey, Amit, thanks so much. Right, I
Thank
feel
you.
honored, to collaborate with you, to have you the first peer. I think you're very empathic, you're very open, you're passionate, and you make this organization, operating system at this organization, very special. So thanks for being with us today.
Thank you very much for the opportunity, and I hope I my answers are of some value to the people who are going to listen. Thank you very much.
Yeah, folks out there, you have heard it, right? Connect to Amit on LinkedIn, or put some question below the comment section, and obviously stay tuned. There's a lot more to come, so stay bold, committed, and open-minded. And we hear us at the next Siemens AI podcast. Cheers.